So in this video, we're going to be looking at combustion reactions in terms of our alkanes. Now, alkanes, we've already said they're going to be generally quite unreactive, where we said the reason why was because, of course, they're going to be non-polar and they have a very high carbon-carbon and carbon-hydrogen bond enthalpy. They've got very strong carbon-carbon and carbon-hydrogen bonds. Now, there's two other reactions that actually take place with our alkanes that we need to know about, and one of them is going to be, of course, combustion. That's why we actually use them as pretty much just fuels. And another reaction is going to be, of course, in the presence of a chlorine or a bromine radical, where we can actually end up with free radical substitution. Now, we're going to be focusing on combustion reactions in this video. There's two different types of combustion reactions you need to be aware of. One of them is going to be complete combustion, and that's when you're burning a substance in an excess supply of oxygen. And another one is going to be incomplete combustion, where you're burning a substance in a limited supply of oxygen. Now, let's say if I were to take the most basic alkane, which is going to be, of course, methane. If I were to take something like methane and react that in an excess supply of oxygen, I would actually end up producing only two products. One of them, which is going to be carbon dioxide, that's a gas. Another one is going to be water itself. Now, if I were to look at balancing this, I normally follow a method where I go CHO, and I say I balance the carbon atoms first, which in this first example, they balance the hydrogen atoms next. I've got 4 over here, so I need to have, of course, 2 lots of water over here that balances, and then I would balance the oxygens, where I've got 2 times 1, that's going to be 2 lots over here, and then I've got 2 lots over here, that's 4 lots of oxygens altogether, and I need 2 lots of oxygen molecules to make that balance itself. Now, you can see here the only products I actually produce is carbon dioxide and water. But what about if I didn't have an excess supply of oxygen? I would end up with methane. That's going to react with, of course, oxygen again, but this time I actually end up producing not carbon dioxide, but instead I actually end up with carbon monoxide itself. I also end up producing water as well, and if we were to balance that using the same method as before, I would end up with, of course, the carbons balancing. I need, of course, 2 lots of water to make the hydrogens balance, and then the oxygens this time it's going to be 2 added to 1 over here. I would actually end up with 3 over 2 or 1.5 lots of oxygen itself. So I've got less oxygen over here, and that's what you can see. And because I've got less oxygen, I actually end up producing carbon monoxide, which we need to remember is going to be a toxic gas itself. So yeah, there's our oxygens balanced, and there's our incomplete combustion reaction for, of course, methane. But the thing is, you can actually end up with even more incomplete combustion taking place. You can end up with methane reacting again, but this time you don't actually produce carbon monoxide, you don't produce carbon dioxide, you actually just produce carbon particulates itself as well, and then water. Now, if I were to balance this again using our method of CHO, the CHO method, I end up with the carbon atoms balancing, the hydrogens, they don't balance, I need a 2 over there. But if I look at oxygen, I've got, of course, here 2 atoms of oxygen, so that balances on its own in terms of oxygen on the left hand side as well. Now, if we look at this reaction over here and we were to compare it to, of course, the previous one, we're actually just using 1 mole of oxygen over here compared to 1.5 to produce carbon monoxide, and the original 2 that we needed to produce the actual carbon dioxide itself. Now, if you were to look at fuel efficiency, this equation over here is going to release the greatest amount of energy, then it's going to be this one over here, and then it's going to be followed by this one being the least amount of energy being released. Now, the general trend is that the more oxygen you have, the greater the fuel efficiency is going to be in terms of the amount of energy that's going to be released itself. Now, one thing to remember as well is that when we deal with branched chain alkanes, we prefer to use these as fuels because they actually have a greater efficiency of combustion itself, and that's just a fact that you need to be able to recall. So anything like, let's say, pentane, right? If I were to compare pentane to something like 2-methyl, and then it's going to be, of course, butane. 2-methyl butane is what we prefer compared to something like pentane itself, because it has a greater efficiency of combustion. Now, I've got a task for you to try. Feel free to pause the video, use the CHO method again, have a go at the following, and resume once you're ready to go over the answer. Just remember, again, if in doubt, always draw the structure out and work out the molecular formula. So yeah, looking at this then, we've got pentane to begin with. We've got 5 carbon atoms. General formula is going to be CnH2n plus 2. So I end up with C5, and then it's going to be H, and then it's going to be 12 itself. That's going to react with oxygen, and we end up in complete combustion, because that's what the question's asking us for, producing carbon dioxide and then water. Now, if I were to balance this using CHO again, the carbon atoms don't balance. I need a 5 over there. The hydrogens, I've got 12 here, so I need 6 lots of water over there. Oxygen, I've got 6 added to 10, that's going to give me 16, so that's 8 lots of oxygen molecules itself. Look at the next one, I've got 2-methyl heptane. So 2-methyl heptane, I'm going to draw this structure out. I've got 2-methyl heptane, which is going to be 1, 2, 3, 4, 5, 6, 7 carbon atoms there, and I end up with a methyl at this position. Now in terms of the number of carbon atoms, I've got 1, 2, 3, 4, 5, 6, 7, 8 carbon atoms in this alkane. General formula is going to be CnH2n plus 2. So I know I've got C, A, and then it's going to be H, and then it's going to be 18 itself. There's a formula of octane, which is the same. It's going to be an isomer of 2-methyl heptane. But of course, I'm going with molecular formula to keep everything simple. So yeah, I would react that with, of course, some oxygen, and I would end up producing carbon dioxide, and then I also produce water as well. Now, if I balance this using CHO, what I actually end up with is, of course, carbon being 8 over here. I end up with hydrogen. That's going to be, of course, 2 times by something gives me 18, or 18 divided by 2, that's going to be 9. And then in terms of oxygen, I've got 9 added to 16. That's going to be, of course, 25. 25 divided by 2, that's going to be 12.5 lots of oxygen itself. And there's that one balance there. So yeah, looking at the next question, we've got incomplete combustion this time of what appears to be propane. That's going to be, of course, the structural formula. I've given the skeletal over here, and we already know that has the formula of C3, and then it's going to be H8. I could have just added up all of these hydrogens together, but of course I want to find it the quicker way. So yeah, in this case I would end up with C3H8. Remember, we've got carbon particulates being produced in this case and water only as our products. So in that case I end up reacting it with oxygen, I end up producing carbon, and I end up with water as well. If I balance it using CHO again, I know the carbon atoms, that needs to be 3 over there, hydrogen, that needs to be 4 over there, and then oxygen, I've got 4 lots over here, nothing in carbon, and so I end up with 2 lots of oxygen itself, and there's that one done. Looking at the next one, we've got 2,2-dimethyl propane, and that's going to be producing a toxic gas and water only. Now in terms of this one, we know our toxic gas is going to be carbon monoxide, and we already know the formula of water as well. Now if you were to look at 2,2-dimethyl propane, what we've basically got is this structure over here, and we've got an isomer of what appears to be 1, 2, 3, 4, 5 carbon atoms pentane. So we know, of course, we can just go with the molecular formula of C5H2n plus 2. We end up with 12. That's going to react with, of course, oxygen, and we need to balance this using CHO again. Carbon atoms, I end up with 5 carbon monoxides here. I end up with, in terms of water, 6 lots of water as well. Oxygen here, I end up with 6 added to, of course, 5. So that's going to be, of course, 11 divided by 2. That's going to be 5.5 lots of oxygen itself. And there's that one done as well. Again, remember, when you're dealing with these, if in doubt, draw them out, find the molecular formula, collate it all together, don't use anything like structural formula, and then of course make sure you follow the CHO method as well.